In a previous video, we learned that there are two laws that govern the behavior of electric current and voltage in an electric circuit: Kirchhoff's current law and Kirchhoff's voltage law. In the last video, we learned what Kirchhoff's current law described. Today, we are going to take a closer look at Kirchhoff's voltage law. This law states that the voltage gained or lost through a closed loop of a circuit must add to zero. As we simplified Kirchhoff's current law, we can simplify this one too by saying what goes up must come down. And that will become apparent to you as we go through and do some examples. To start exploring this law, let's draw a simple circuit with a 12-volt battery as a source of potential. This will cause current to flow through the circuit. The question that we will pose is, what is the change in voltage across resistor R? Well, let's start at a certain point along the circuit that is just before the battery and label this as 0 volts. We'll also call it point A as a reference. As we travel in the direction of the current, each coulomb of charge that passes through the resistor will gain 12 joules of energy. That is, the energy gain is 12 joules per coulomb. The voltage is sort of like a height, and in a sense, we can say that we go up 12 volts of potential. We can say the position in the circuit directly above the battery, labeled point B, as having 12 volts of potential. As we continue to travel along the circuit in the direction of the current, let's designate another position right above the resistor as C. The potential at this position still has 12 volts of potential because the charge in the current has not lost any energy. However, as current travels through a resistor, the energy contained in it will be transferred to heat and lost to the surroundings. How much energy will be lost per coulomb of charge that passes through the resistor? Well, that is the same as asking, what is the change in the voltage across the resistor? Which is our original question. Let's take a look at a position just below the resistor, point D. Now we can see that points A and D are on the same voltage level because the current does not go through any elements, a battery, a resistor, a lamp, or any other thing that might produce or use energy between those 2 points. This means that the potential at point D is 0 volts. So, the voltage change from C to D is to go down 12 volts. So we say the voltage change for resistor R is negative 12 volts. Let's look at an analogy. Say that we have a staircase that goes from a lower level to an upper level. We'll say that this staircase increases by 12 meters. We are comparing this height to, say, a 12 voltage increase in electric potential, like the example we just did. Let's introduce a stick figure, Charles Augustin de Coulomb. Yes, he is the dude who the unit of charge, coulomb, was named after. We are going to designate the location Mr. Coulomb is currently standing as position A, and that the bottom of the stairs is 0 meters. Let's suppose that Mr. Coulomb walks up our 12-meter staircase. Okay, let me make him do that. It's kind of bouncing. His height would increase by 12 meters, right? We'll say at the top of the staircase is position B, and that's at an elevation of 12 meters. Now suppose he walks along the top to another position we're going to call C. You can see that he has not lost any energy because he is moving horizontally along the top of the walkway. Now suppose Mr. Coulomb comes to a slide and goes down it to a position we'll call D. So now he's going to slide down to position D. Let's ask a question. What was Mr. Coulomb's change in height in going down the slide? You might think the answer is obvious, and it really is. Since he was 12 meters off the ground at position C, and seeing that position D is the same level as position A at 0 meters, the change in height from C to D is negative 12 meters. And if he went and continued the loop to A, you can see from the beginning to the end, his height didn't change at all. In the same way, voltage doesn't change if you go in a whole loop around a circuit. So in conclusion, let's take a look at this. So for the most part, when electric current goes through a battery, the potential increases. And when it goes through a resistor, it decreases. The amount of voltage in a full loop of a circuit must add to 0. And you can see in this particular circuit that if we go up 9 volts, we come down 4 volts, we have to come down another 5 volts in order to get back to 0. The whole loop adds up to 0, and in this way we can find missing voltage changes for different elements within a circuit.